Let's see some properties which are useful in deriving the congruency rules more further. So what are the different properties connected with triangles? Let's see in brief in today's session, because properties play a vital role in proving many rules, the congruency rules of two triangles, to be followed with isosceles property. Triangle properties. The first property is isosceles property in mathematics. What is an isosceles property? Isosceles, the word isosceles means that any two sides of a triangle are equal. Then the triangle is called isosceles triangle. So initially we know that a triangle is isosceles if the two sides are equal. That is, triangle ABC is isosceles if AB equals AC. If any two sides of a triangle are equal, then that triangle is called isosceles. Is how we understand the isosceles property connecting the triangle. Two sides equal implies the triangle is isosceles. Now let's see the isosceles property connecting the angles. Now that we have defined that a triangle ABC is isosceles if any two sides of that triangle are equal, now let's see how we can connect that with angles. Imagine I have an isosceles triangle A, B and C. The triangle ABC is isosceles in the sense the sides are equal. Then the isosceles property connecting the angles says that if the two sides are equal, then their corresponding angles, that is this and these, must be equal. When two sides are equal, their angles must be equal. Therefore, isosceles property here states that if two sides of a triangle are equal, then their corresponding angles must be equal. That is, if this side equals this, then this corresponding angle of this side must be equal to then this corresponding angle of this side. Then their corresponding must be equal. That is, AB equals AC implies angle B equals angle C, implies angle B equals angle C, is how we connect the isosceles property. This equals this implies this equals this. Isosceles property connecting the sides with angles. Given that two sides equal, their corresponding angles must be equal, is how we define isosceles property connected with the triangle ABC. Now that we have discussed about the isosceles property connecting the angles, now let's see the isosceles property which connects the sides. Let's see how the sides can lead to the connection of isosceles property in terms of angles. This is something like the reverse process of the previous session. Isosceles property connecting sides of the triangle. As in the previous session, we have seen that when two sides of a triangle are equal, their corresponding or the sides opposite to those angles are equal. Let's see what if the two angles are equal in a triangle. Will it still be isosceles? Is the biggest question out here. Therefore, when I have a triangle ABC in which the two angles are equal, I have a condition where angle B is equal to angle C in case of this triangle ABC. Will the two sides be equal according to the isosceles property is what we are going to see in the session. Now, as we know that in triangle ABC, angle B equals angle C. Then isosceles property equally says that if the angles are equal, the sides opposite to those angles, this side opposite to this angle and this side opposite to this angle must be equal. AB must be equal to AC. The side opposite to this angle and the side opposite to this angle. That implies by isosceles property AB must be equal to AC. Is how I define the isosceles property connected with given the angles sides are equal or given the sides angles are equal. Therefore, my property equally defines if the two angles of a triangle are equal, then the sides opposite to those angles, like this side being opposite to this angle and this side opposite to this angle, then the sides opposite to those angles must be equal. This is how I define the isosceles property connecting the sides. Given the sides, the respective angles are equal. Given the angles equal, the respective sides are equal. Is how we define the isosceles property. Now the next type of congruency rule which you're going to learn is about SSS congruency rule. Let's see the triple S congruency rule as connected with the branch of mathematics. As can be clearly seen that SSS refers to all the three sides of the two triangles. It doesn't take into consideration any angle but only the sides. Is how we understand the rule initially with SSS congruency rule. So let's take two triangles. Triangle ABC and triangle DEF. Here, let me say the side AB equals side DE. One pair of side is equal. Let me go to the second pair of sides. BC equals EF, and the third pair, which reference with third S, is AC equals DF. Then triple S axiom or triple S congruency rule states that if the corresponding sides of the two triangles are equal, then the triangles must be congruent by SSS. AB equals DE, BC equals EF, AC equals DF. The first side, second side, and the third side. So if the corresponding sides are equal, then by triple S axiom, triangle ABC must be congruent to triangle DEF. Is how I understand the two triangles being congruent through the side axiom. So let's write this in statement. If the corresponding sides of two triangles are equal, then the triangles must be congruent. Is how we understand the triple S axiom connected with the two triangles being congruent. Side axiom. Now that we have seen the various types of axioms which prove the congruency of two triangles with their own respective rules and properties, now let's see exclusively when we consider two right-angled triangles. The congruency proved through the properties using for two right-angled triangles. So the Rhs axiom derived for two right-angled triangles. Rhs R stands for right angle, H stands for hypotenuse, and S stands for one side other than the hypotenuse. So right angle, hypotenuse, and one side of a triangle are taken into consideration in proving the congruency of two right angled triangles. So let's see the Rhs axiom connected with congruency of two triangles. Imagine I have two right angled triangles. Say I consider the right angled triangle ABC and the right angled triangle DEF. This is right angled at B and this is right angled at E. Now imagine I have my angle B which equals angle E, which are right angled, and clearly my hypotenuse here is AC because this is opposite to 90 degrees. So AC is the hypotenuse for the first triangle and FD is the hypotenuse for the second triangle. So if the two angles are right angles and if the hypotenuse are equal and one side which is equal, say my BC is equal to ED, then by right angle, hypotenuse and side, right angle, hypotenuse and side, I can say that the two triangles are congruent. If angle B equals angle E, which is 90 degrees, and my hypotenuse AC equals my hypotenuse FD, and my side BC equals my side ED, by Rhs axiom, I can say the two triangles are congruent. Then by Rhs axiom, triangle ABC is congruent to triangle DEF, is how we understand the Rhs axiom. Two triangles congruent when they are connected with Rhs axiom. Let's see in words. Rhs axiom. If in two right angle triangles, right triangles, the hypotenuse and one of the sides are equal, the corresponding hypotenuse and one of the sides are equal, then the two triangles must be congruent, is how I understand the Rhs axiom. If in two right triangles the corresponding hypotenuse and one of the sides are equal, then the two triangles must be congruent, is how we understand Rhs axiom. Right angle, hypotenuse and one of the side being equal makes the two triangles congruent to each other. Now that we have seen the different types of congruency rules, let's investigate what if the corresponding angles are equal. As we have seen the triple S rule, where if the corresponding sides are equal in the two triangles, then the two triangles are congruent to each other. Similarly, will the two triangles be congruent if their corresponding angles are equal? Is the biggest question in the session. So let's investigate triple A rule for congruency of two triangles. Triple A rule. What is triple A rule? AAA stands for all three angles of the triangle. So imagine I have two triangles A, B, C, and I have another triangle D, E, F. If my angle A equals angle D, angle B equals angle E, and my angle C equals angle F, then will the two triangles be congruent? We can clearly see that if the corresponding angles are equal, then the two triangles may not be of the same shape. We can just draw random triangles using a protractor and the ruler and check if we can have the same angles and different sizes of the triangles. Just like here, the angles are equal, but the triangles are not of the same shape, clearly indicating that these two can never be congruent, never be equal in all respects. Therefore, if angle A equals angle D, angle B equals angle E, and angle C equals angle F, then by AAA rule, triangle ABC is not congruent to triangle DEF. It is very important to note the corresponding angles equal implies the two triangles need not be congruent. Therefore, if corresponding angles are equal, then the two triangles need not be congruent. Not always. Only few times the triangles are congruent, depending on their respective lengths, but they are not always congruent. Since the two triangles form a different size, though their respective angles are equal, is one of the biggest mathematical property which should be noted. The reason being that since the two triangles form a different size, though their corresponding angles are equal, they form a different size, this being small and this being big. Or any triangle which is so smaller in size and so bigger in size will have the same common angle, but they are not congruent to each other. The two triangles have corresponding angles equal, but they are not congruent to each other, is how I understand the learning outcome of AAA rule. Congruency connected with AAA rule. Angle, angle, angle rule. Now that we have learnt about congruency rules connected with congruency of two triangles, let's apply the rules in real life. Today's session is about applications of congruency rules in solving mathematical problems. Applications of congruency rules. All SSS, ASA, SAS, RHS, AAS are the various types of congruency rules which we have discussed till date. So let's apply into the problems. Given, for example, I have a triangle, say for example, I have a triangle A, B and C, and let me say the altitudes of the two sides are equal. That is, when I take the altitude from B to AC, this is the perpendicular dropped onto the side AC, is how we define altitude. the altitude from B to AC is BD, and similarly let me drop an altitude from C to AB. Say here. So I have an altitude which is CE. Is how I understand the altitudes BD and CE. Now let's connect this with the question which says the two altitudes are given to be equal. Prove that for the given triangle with equal altitudes, AC and BD, the triangle is isosceles. This is the question I have. Given that the altitudes are equal, I had to show that the entire triangle is isosceles. Let's see how we can define the isosceles property using congruency rules. Now let's try to prove the isosceles property using congruency rules as we have learnt in the previous session. As clearly we see that ABC is a triangle and EC and BD are the altitudes which are given to be equal. In triangle ABC, it is given that the altitude EC equals BD is given, and angle D BDA is equal to CEA, which is 90 degrees, is how we have the two properties connected with the given problem. Now let me take the two triangles BEC and CDB and see, and so that we prove that they are congruent. Let's consider BEC and CDB and prove that the two triangles are congruent to each other. Let's take triangle BAC and triangle BDC. So in these two triangles, clearly I have BD equals EC, or my EC is equal to BD, since it is given that the altitudes are equal. So the two sides of the two triangles, triangle BEC and triangle BDC, must be equal. Next, I have this to be 90 degrees. Therefore, my angle the other side also must be 90. Therefore, angle BEC is equal to angle BDC, which is equal to 90 degrees. As how I see the perpendicular altitudes. Similarly, if I take the triangle BEC, my side BC is nothing but the same side for the triangle BDC. That is, the side BC is the common side for triangle BEC and triangle BDC, and hence obviously they must be equal to each other, equal to itself. BC of the triangle BEC must be equal to the BC of the triangle BDC, since it is the common side, and this being since altitudes. It's very important that we write the reason for what we write out here. The reason here being their altitudes. Because it's altitudes, it's equal to 90. This equals this because it is given, and this equals this because they are the common sides for the two triangles, triangle BEC and triangle BDC is how we understand the property. Next, clearly I see that this is the right angle and this is the hypotenuse and this is the side connecting the two triangles. Therefore, the right angle, the hypotenuse and the sides being equal makes me recollect the Rhs axiom. Therefore, by Rhs axiom, right angle, hypotenuse and side, I get the property which you have learned in the previous session. By Rhs axiom, triangle BEC is congruent to triangle BDC. Therefore, when I prove that the two triangles BEC and BDC are congruent, indirectly I mean that the two triangles are equal in all respects. Therefore, this triangle is equal to this triangle in equal respects. We utilize this triangle concept now to prove that the two triangles are isosceles. So let's see how we can prove the isosceles property for two triangles. Imagine I continue here that area of triangle ABC is equal to triangle ABC because the two triangles are the common triangles. So this being the common triangle, they are equal to each other. Now, as I see here, my triangle ABC can be split as AEC plus BEC. So this triangle can be split as triangle AEC plus triangle BEC, as can be clearly seen here. Similarly, on the right hand side, my triangle ABC can also equally be split as AEC or ABD plus BDC. So I split it as ABD plus triangle BDC is how I split the two triangles, being congruent to each other. Now clearly I proved that triangle BAC is congruent to triangle BDC, which are equal in all respects. Now because these two triangles are equal, I can cancel the two triangles which are exactly equal in size. So two equal quantities can be struck off on the two sides of the equation. Therefore, triangle AEC is congruent to triangle ABD. So indirectly I get my triangle ABD and AEC are the two triangles which are congruent to each other. Therefore, they are equal in all respects. Now since the two triangles are equal in all respects, their side AB must be equal to side AC. Therefore, AB of triangle ABD must be equal to AC of triangle AEC. So AB equals AC equals AB. Therefore, this AC which connects the whole triangle ABC is indirectly equal to the side AB connected to the whole triangle ABC. Therefore, for triangle ABC, side AC is equal to AB. That implies the two sides are equal and hence the triangle is isosceles. That implies triangle ABC is isosceles triangle, is how I conclude the proof using congruency rule. If a triangle has two equal altitudes, then the triangle must be isosceles. is how I make the learning outcome. Therefore, my learning outcome here is that if a triangle has two equal altitudes, then the triangle must be isosceles, is how I understand the learning outcome. If a triangle has two equal altitudes, then the triangle must be isosceles, and this can be proved using congruency rules, what we have learned in the previous session. Applications of congruency rules connected with the properties. Now that we have discussed about congruency rules and the applications of congruency rules in solving or deriving many mathematical or geometrical properties in mathematics, now comes the concept of the unequal angles and unequal sides connected with the geometry of triangles. Before we get into the unequal sides and unequal lengths of the triangles, let's get into understanding the basic concept of the length of the side connecting the size of the angle. Length of side versus size of angle. So let's see how we can connect the length of the side of a triangle with the size of the angle as that made. Before we get into understanding this, let's take a smaller line. Imagine I have a tree out here, or this is a palm tree which I have out here. So imagine this as the palm tree which I have, and I'm standing out here to watch the palm tree. Now I have an angle, so this angle is theta 1. Imagine I have a second case where I have a small bush and I stand here to the same distance and then watch the bush out here. So this angle is theta 2. Then what do we observe from these two real life situations? Here is the palm tree, and say I have one more case where I have an Eiffel Tower out here. And I'm at the same distance watching the top of the Eiffel Tower. I have three cases: theta 1 where I observe the top of the palm tree, theta 2 where I'm at the same distance and observe the top of the bush in the lawn, bush in the park, and I'm at the same distance where I observe the top of the tower from the distance, which is theta 3. How do you connect the relation between angles theta 1, theta 2 and theta 3 is the biggest question out here. How do we connect? As we can understand through real life situation that bush is smallest of all the three sizes as compared here. Bush is to a height of this, and a palm tree would be around 30 to 40 feet, and an Eiffel Tower, which is very tall, more taller than the apartments and the buildings. So here we know that this is of a greater height, this is of the next greater height, and this is the least of all the heights. Therefore, the one which is the least of all the heights makes the lesser angle. The one which is greatest of all the heights makes a greater angle. Therefore, here I understand that theta 2 is the smallest angle, because since size of or height of bush smaller, and theta 3 is the largest angle. Because height of tower, since tower is the tallest of all the three different situations which are taken, out of the bush, the palm tree and this, the tower is the tallest. That's how we understand the connection between the bush, the palm tree and the Eiffel Tower. Therefore, the least of the all angles theta 1 and theta 2 and theta 3 is identified to be theta 2, which is the smallest angle, simply because the height of the bush is smaller, and theta 3, which is the largest angle, because tower is the tallest and the bush is the smallest. Is how we understand the relation. Therefore, connecting the inequality with the angles here, I clearly see that theta 2 is smaller than the angle theta 1. Next comes smaller than theta 3. Is how I connect the real life situation with the angles. Lesser the angle, lesser the side, or lesser the side, lesser the angle opposite to it. As how we have the triangle connected with the angles of different heights. Now let's use the property of connecting the size of the angle and the length of the side to a triangle ABC. So let's take inequalities in a triangle as the topic connected with triangles in the session. Inequalities in a triangle. So let's see how we can connect inequalities in a triangle. Imagine I have a triangle out here. Then let's take the case of the triangle ABC. Now clearly I can see that angle A is smaller than angle B, which is obtuse, and this being acute. Therefore, the property here says that the side smaller the angle, smaller is its length of side. Larger the angle, larger is the length of its side. Therefore, this being a smaller angle, BC is the smaller side, and angle B being the biggest or the obtuse, AC is very long. Smaller the angle, smaller is its opposite side. And similarly, larger the angle, larger is its opposite side. Therefore, in the triangle ABC, I find that angle A is less than angle B. Implies smaller the angle, smaller is its opposite side. Therefore, the opposite side of A, which is BC, must be, the length of BC must be shorter than the length of AC. Is how I understand the property connecting the angle of a triangle and the sides opposite to the angles. Smaller the angle, smaller is its side. So the property finally concludes that the angle opposite to the smaller angle is the smallest side in a triangle, or the side opposite to the smaller angle is the smallest side in the triangle, or the side opposite to the largest angle is the largest side of the triangle, is how we connect the property. Connecting smaller the angle, smaller is its opposite side. Larger the angle, larger is its opposite side, is how we understand the concept connected. Inequality in a triangle. Now let's see a property which connects the sides of the triangle, the three sides of the triangle. Imagine I have a triangle A, B and C. ABC is a triangle in which the three sides are AB, BC and AC. So what is the property which connects all the three sides in a triangle? This property is one of the most important property in the inequality properties in a triangle. So let's see the property connecting the three sides of a triangle. For this triangle ABC, there are three sides which are AB, next is BC, and then the next is AC. So AB, BC and AC are the three sides of the triangle. So using these three sides, let's see how the geometrical property connects. It clearly says that suppose I want to take BC and I want to take sum of the other two sides AB plus BC. Then how do I relate the three sides AB, BC and EC when the sum of two sides AB and BC are connected with the third side AC? Mathematically, the property says that the sum of two sides will always be greater than the third side. This may be true if you take BC and AB or BC and AC. That is, AB plus AC will always be greater than BC. So if I take the two sides AB and AC, then the sum of these two sides must be greater than the third side BC. Next, if I take the two sides BC and AC, AC plus BC must be greater than AB, is how I see the properties connected with this. Is how we understand the sides connected with inequality. So this is called triangle inequality. Inequality which states that sum of two sides of a triangle exceeds the third side. or exceeds is always greater than the third side. Therefore, sum of two sides of a triangle always exceeds the third side. Is how I connect the triangle inequality in the triangle ABC. Sum of two sides exceeds the third side. Triangle inequality. AB plus BC greater than AC, or AB plus AC greater than BC. AC plus BC greater than AB. That's how we see the triangle inequality. Now that we have seen the triangle inequality, will the inequality be true if it is equal? Let's see the investigation of triangle inequality reduced to equality. So for example, I have a triangle A, B, C. Will sum of two sides be equal to the third side? Is how we see. Clearly, I can see that when I take AB and BC, when I add the two sides, then obviously it must be greater than but can never even be equal to AC, the third side. Because for a triangle, a closed three-sided figure to be formed, we need to have the condition that when you add two sides of a triangle, its third side must be less, cannot be equal or greater than. Therefore, when this is strictly greater than is how I understood. Therefore, AB plus BC, it is important to note that AB plus BC, it can never be equal to AC. It should be strictly greater than. Therefore, my learning outcome out here is that sum of two sides of a triangle can never be equal to the third side, because in that case it cannot get a closed three-sided triangle, because it fails the condition of forming a closed three-sided figure, that is the triangle. It fails the condition of forming a closed three-sided figure, or it form an open triangle, is how we understand the strictly greater than concept connected with sum of two sides always exceeds the third side. At the most, it cannot be even equal to or less than. Is how we understand the triangle inequality strictly following the strictly greater than inequality. Is how we connect the triangle properties with inequality.